So Tyler Hanks is going to talk about a compositional framework for convex model predictive control. Here you go.
Talk about model-predictive control. So this is probably an applied category theory talk, which is, I think, a good thing since it's the last one. Probably will. I work with all of these lovely people on screen. Okay. So model-predictive control is a modern. Is that better?
Yeah.
Cool. Okay. Yes. So model predictive control is a modern and very capable paradigm for doing optimal control. So it can do awesome things like propulsively land building-sized rockets, as an example. However, there's a caveat, which is that it's often very complicated to actually implement. So this giant block of code here is a tutorial example of implementing, setting up an MPC problem in this MATLAB framework called Casati. It's long. So by contrast, here is how you set up a similar problem in our applied category theory informed implementation. And so you'll notice that it's significantly shorter. And so my promise to you is that by the end of this talk, each and every one of you will understand how we leverage category theoretic abstractions to achieve this implementation. So yeah, basically we're just going to sort of lay out what MPC is and how it has this sort of inherent compositional structure. And we're going to talk about how we can model that category theoretically. And then I'll wrap up by talking about some additional things that we can do with this framework. Yeah, so what actually is model predictive control? How does it work? Essentially, it's a form of feedback control, right? So you have some system that you want to control. You are allowed to feed it some control inputs. You're allowed to look or observe the state or some measurement of the state. And so in model predictive control specifically, you feed the state back into some sort of black box optimization system. You have some implicit model of the system. And essentially what you do is you solve an optimization problem that is meant to sort of model the response of the system to control inputs. So you use your model of the system to essentially predict how you think the system will respond to your control inputs. You choose the best input for some given prediction horizon, and then you feed that into the system, and you just keep doing this in a loop until eventually, you're trying to track some sort of reference trajectory, for example. So how do control theorists actually formulate such a process? Typically, the way that they set it up is in terms of a mathematical program or a minimization problem. So here we see a couple different components. So I'll say the xi's are meant to be the state of the system. The ui's are the control inputs that we're feeding to the system. And we have sort of three main components, right? We have this function L, which is sort of the loss function that you're trying to minimize. So this could be tracking some reference trajectory, trying to get to the origin of some coordinate system, etc. You're minimizing a sum of that function over your look-ahead horizon of n. And then the other component is this sort of discrete dynamical system, right? So this is your FD. So this is a discretized, model of your system, and this is sort of forming an equality constraint to your problem. And then the last component is this G, which can encode sort of arbitrary constraints. So these could be things like actuator limits. You don't want to, use an infinite amount of thrust. That would be bad. So for us, we're going to be focusing specifically on the case where our objective function and our constraints are convex, and our system that we're trying to control is affine. And the reason why we look at those cases specifically is that when all those conditions are met, the whole optimization problem is actually a convex optimization problem, so we can solve it very efficiently. So there's this sort of sense in which this big control problem here is sort of, you can look at it as if it's this single subproblem sort of repeated over your finite prediction horizon, right? So there's this sense in which we're repeating, for some definition of repeat, this subproblem n times. And so that's sort of the structure that we're trying to formalize. So yeah, just to spell this out a little bit more clearly, basically, if we consider one time step of control on the left, we're taking in some fixed input. We want to choose a control input to get us to a next state of our system. And then in the next subproblem, we're taking that state that we've computed and sort of pushing it into the new subproblem. So yeah, this composition pattern can be modeled category theoretically, unsurprisingly. So how do we do that? Oh, well, yeah, so we want to compose these systems to sort of get this like two-step time horizon problem, right? So traditionally or historically, this path is kind of how control engineers did this, right? They took their control problem, they did some sort of translation into a convex program, kind of by hand typically, and then they took their convex program and they actually wrote it in some code framework to get something that they could solve. Alternatively, the approach that we're advocating for is that you instead take this bottom path here. So we're going to take our control problem, we're going to use this to generate some like sort of generating endomorphism in this category called para-conv. And then we're going to compose this morphism with itself n times to sort of build up our n-step optimization problem. And then we can automatically compile such a morphism into code. So sort of the emphasis is that historically, the top path is often done by hand, it's labor intensive, it's prone to errors, etc. Whereas the bottom path, really only the first sort of generate arrow has to be done by hand, and everything else can be automated. So yeah, to actually do this, we need to talk about categories for looking at convex optimization problems. This, if you were in attendance during Richard Samuelson's talk, I believe he talked about some of this stuff. So some similarities here. So yeah, to recap, we have this intuition that repetition looks like composition, and we're saying we need some sort of data structure to sort of package up our optimization problems in a way that's amenable to composition. So first, to get there, we need to talk about how we actually represent optimization problems in terms of like just a function. And so the way we do this, the sort of weird thing about constrained optimization problems, right, is that you can violate your constraints. And so you need a way to encode that mathematically. The way that is typically done is taking functions that are valued in this symmetric nodal poset called the extended reals. So this is the reals union with positive and negative infinity. And so you use positive infinity to encode a hard constraint violation. And so that sort of informs you as to why adding infinity and negative infinity still produces positive infinity, because if you got an infinity, you did something very bad, and so that shouldn't vanish just because you like did infinitely well in your minimization. So now that we have that out of the way, we can talk about these things called convex bifunctions. So these were introduced in Rockefeller's seminal work all the way back in the 70s. They haven't really been used very much until now, or the category theorists have kind of started to pick them up as a useful concept. So a convex bifunction is just a jointly convex function of the form Rm cross Rn into, that should say, R union plus minus infinity, but it doesn't. And so the reason why these convex bifunctions are useful is because we can essentially use them to like package up, in some sense, a convex program, and specifically a convex program that is subject to like perturbations in the first variable. So if we take sort of this generic convex optimization problem here, you want to minimize some objective functions subject to constraints, and these constraints, importantly, are being perturbed by this variable w coming in here. So we can package this up as this convex bifunction here, where we're using these deltas. These deltas mean like the convex indicator function of that constraint. So this is like send to positive infinity if this constraint is violated, send to 0 if it's not violated. So if the constraint is satisfied, it has no outcome on the objective. If it is violated, the whole thing goes to infinity. So that was sort of the engineered definition. Here is the abstract nonsense definition. A convex bifunction, you can think of it as an R-bar enriched profunctor, where you're looking at the domain and codomain as discrete R-bar categories. Yeah, if that makes sense to you, that makes sense to you. And so, but since we have these enriched profunctors, right, there's a natural way to compose them. So the formula for enriched profunctor composition is we take the coproduct over the shared variable between the two of the monoidal product. And so when we specialize that to the case of R bar, we get, you know, sum the functions and take the infimum over the shared variable. And so importantly, if f and g are both convex, then doing composition of f and g is also convex. So these convexity is closed under bifunction composition. And so this sort of naturally obviously gives you a category where objects are, you know, Euclidean spaces, your morphisms are your convex bifunctions, your composition is what I just said, your identities are like the convex indicator of the identity in rel, and your symmetric monoidal structure is inherited from R bar. So bifunction composition, right, it sort of gets us this notion where the decisions that I take in one problem become like perturbations to the next subproblem, right? Because we're like using the y, which is thought of as the decision variable for f, as the perturbation to g. And so this sort of recaptures this intuition that the states are what are coupling these subproblems together over time in our MPC formulation. And so this is nice, but the question is, you know, if we go back to the MPC formulation, it was a ways back, I guess. So we had that the states are coupling across time, but we also had these control inputs, right, which are essentially independent to each problem. So the question is, how do we model that category theoretically? The answer is that we use this thing called the para construction. So if you're familiar with this paper, Categorical Foundations of Gradient-Based Logic, you know about this. It's pretty simple. Basically, given some symmetric monoidal category, we can form this parameterized version of it. It just has the objects are the same as those in C, but then morphisms are pairs where you pick some object U to be the like parameter space of the function, and then the second thing in the pair is a parameterized function, parameterized by U, right? And so you can compose these parameterized functions in sort of the obvious way. And then the identity is just the identity function, and you take the monoidal unit as the parameter space. So how does this actually get us our control inputs? Basically, we can use the para construction, and this essentially just gives us, well, now we have a bifunction with some parameter, so that's going to be our control input. And so yeah, we can take our one-step subproblem here, package it up as a bifunction. Again, these deltas are indicator bifunctions. And then we can start composing this thing with itself because we now have an endofunctor in this category, or endomorphism in this category. So yeah, sort of the main kind of result of this section of the talk is that composition builds MPC problems. So essentially, getting some generating endomap G in this category gives us a recipe to like build up an n-step MPC optimization problem. So that's, kind of nice. And so now we can turn back to the code example that I showed at the beginning and kind of dissect and understand it a little better. So we have, our cost and dynamics and constraints just encoded as normal Julia functions. And then we can take those and form this one-step bifunction, this generating parameterized bifunction in this category. And then, to form, so we pick our prediction horizon to be 10 arbitrarily. And if we want to form our MPC bifunction, we just, compose n copies of this thing with itself. And then, of course, we can actually send it to a convex optimizer and solve the darn thing. So this is this is the spectrum of scientific computing technology. I would just like to emphasize that now that we have sort of an explicit representation of these things in code, the question is, well, what more can we do with it beyond just recovering like traditional MPC problems? So yeah, what are these like? It wouldn't be much of a compositional framework if we just recovered traditional MPC. So let's see what else we can do with it. So the first cool thing and sort of necessary thing if you really want to do model predictive control is you need to be able to model things like initial and terminal constraints. And these can be modeled very easily and nicely symmetrically as just bifunctions either from R0 or to R0. So like this bifunction on the left, you can use this to encode like picking out a specific x naught as your initial condition. And then on the right, you can use this to encode any sort of like terminal state constraint, like saying, I want my state to be this at the end of this process. The other nice thing about convex bifunctions is that they actually form this thing called a pro-arrow equivalent of vect. For those of you who don't know what that means, that is basically just a way of building a double categorical structure on top of this single category called vect. And so, yeah, basically we have the vertical arrows are just the linear maps, but then our horizontal arrows are the convex bifunctions, and we have cells are given by essentially like pointwise relaxations. So like inequalities between the top cell and the bottom cell. And the reason why it's a pro-arrow equipment is because we can basically, and I think Richard mentioned this in his talk, we can sort of lift uniquely any given linear transformation into a convex bifunction by taking the indicator of that linear transformation, which is just given by that. So these form the companions and conjoints of this pro-arrow equipment. And the reason why that's useful is because we can now start to express things like sort of sequential control problems. So if I want to express something like, well, first I want to navigate to a table, then I want to pick up a glass of water, that might be modeled by something that would look a little like this. So, P1 is sort of our problem for getting to the table, and then we lift some linear transformation A into a convex bifunction to sort of say, well, the output that, like the state that I reach at the end of this process, I want to transform that in some way to become an input to the next state of the problem, which will help me pick up my cup of water. And then finally, there's using this similar graphical calculus, we can sort of express controlling coupled systems. So on the left, I'm sure a lot of you have seen this kind of thing before. This is like the operad of undirected wiring diagrams, we're filling these circles in with dynamical systems. And so we're saying we have some system F and some system G, and they share some boundary state Y. And so if we want to sort of take that and translate that into a control process that will control that joint system, we can sort of use some canonical copying and merging operations. So the black dot is copying and the white dot is summing, actually. So that would be like the sum in graphical linear algebra, but taking the convex indicator of it. So yeah, future work. Obviously, it's all well and good to build up these massive problems, but the sort of thing that you really want to work towards is a way to actually then exploit that problem structure to sort of give like a compositional semantics for solvers. And this, there's well-known ways of sort of exploiting similar structures, and it'd be nice to get a categorical story for that, and that's sort of what I'm working on right now. Another potential direction is to sort of generalize this to non-convex problems. So there's like nothing inherent in this framework that restricts, like there's nothing that says you need to be doing this on convex problems. We just chose to do it on convex problems because those are nice problems that solve quickly. And then finally, I think it'd be nice to sort of fit this into the larger framework of like compositional dynamic systems, a la Spivak and yeah. So in conclusion, we prove that classic MPC optimization problems are composites of endomorphisms in this category of parameterized convex bifunctions. So this sort of gets us this nice diagrammatic language for constructing more complicated problems. Then we leverage these results to build out a software library, which is open source, I should mention. And you can see this preprint on arXiv for more details. And of course, we are using this to push the Pareto frontier of usability, generality, and performance in scientific software. So now have some safe travels.
Any questions? Okay.
I have a question. How do I do this?
Yeah, I think so. Or
Okay, I don't really have a question. I just got to say, as a control theorist, I'm pumped.
okay, sweet. Nice.
Okay, go ahead.
So I've looked at the algebraic control library, and there's a module called lenscats. And so I'm just curious if you've been able to extract a category of lenses out of convex bifunctions.
I think so. We can talk about this more, but this was all experimental, and I don't know if it's actually a formal like functor or anything yet. But yeah, we can talk about it more. Unclear is my answer. It's an experiment. Yeah.
All right. Thank you very much.
How do you determine the number of steps to compose? Because that's a very important part of what you're doing.
Right, yes. The answer to that question is it's art. So control theorists get really good at this, or they do a lot of experiments to figure this out. I would say that one of the advantages of this framework is it's obviously very agnostic to your choice of time step. So, choosing a different time step just amounts to a different amount of compositions. So it's kind of easy to, you still have to, it doesn't make that choice for you or anything, yeah. Right, exactly, yeah.
So one question and one comment. The question is whether you've put any thought into trying to build the constraints directly into the objects and thereby kind of force them into the diagrams already. The comment was that this kind of like end step look ahead seems like it could be a really promising place to look for failures of compositionality that were in Katerina's talk earlier.
Yes, yeah, so I'll address the comment first because that's actually a really good point, and I kind of forgot to mention this. My advisor is probably mad that I forgot to mention this, which is yes, in general, you can't just, like, the solutions don't compose, right? So you can't just solve the one-step problem and then like take the output and plug it into the next sub-problem and expect that to be optimal, you know? So that is a failure of compositionality. So yeah, the way that control theorists work around this is there's, you know, different algorithms for sort of solving these things in like a distributed or a fashion that like takes advantage of the structure without, you know, just solving one step, solving the next step, etc. And then to answer your question, I would say, yeah, it's definitely an interesting idea to like bake the constraints into the objects. I think it's kind of like, it's just a choice that we had to make. And I think one of the reasons why we made this choice is because we liked this nice notion that the convex bifunctions form a pro-arrow equivalent over vect. And so obviously you would kind of lose that if you're saying that your objects are no longer vector spaces, they're like some sort of convex spaces. Or at least I think you would lose that. Maybe I shouldn't say that so confidently. But yeah, I think it's kind of just a choice. And I think it would be interesting to look at baking the constraints into the spaces. Yeah, thank you.
Any more questions? And then I'll give it up for Tyler then.